Hi, Jacob. How are you? Hi, Jose. Hi, Emma. Sarah. Happy Monday. Yay, I know. How's everybody doing? I'm good, thank you. Yes. What about the sign up sheet on the Google for your team? Let me see. Let me check it. Looks like some people have signed up. Only 3 teams. So if you are looking for team members or you know someone you want to work with, you can sign up there. Okay. My other class, I require group work, so they have signed up. But in this class, there are only 3 groups that sign up. So if you know someone that you want to work with or you're looking for someone, you can put your name on there. And then people can add. And then maybe communicate with each other, send each other email or phone number you can text or Discord link. You can use Slack as well. I use Slack with my cybersecurity student competition team. In March, they competed. Okay. Well, we have a couple minutes. So think about if you want to work on teams for your project. And then look at your lab and your assignment. I mean, your assignment and your notes. And then the lab will touch on that on Wednesday. Okay, let me go in. So check out your notes for now and your assignment. We'll do encryption today. If you have any question right now, let me know before class starts. So we are approaching the end of the semester and the end of the book. Yeah, Rashad is looking for team members. So if you are interested, okay, so it's 6 o'clock. I'll go ahead and get started. So in this week, we are going to talk about encryption. I posted a few things in announcements for extracurricular stuff if you're interested. For the summer, I am teaching a few non-credit courses. They are short and sweet. If you finish the whole series, you can get a certificate and a batch for the certificate and batch for each of the course. And that way you can link it on your LinkedIn account. I am doing the IoT series, which is Arduino and Raspberry Pi. Some of that would also be available for some high school students that are junior and senior. Normally, I do coding camp with them, but since I'm teaching non-credit in the afternoon, I won't be able to do coding camp with them. So um, they will likely be able to join the non-credit. But if you're thinking of getting Microsoft Office certifications, non-credit classes are free. I'm also teaching one CIS30A, which is Python class in the summer. I had given up my Java class to another faculty that needs a class, so I will not be teaching 18A this summer. In the fall, I am teaching the Python series along with the cybersecurity courses, and hopefully I'll be able to get some of the flyers out later as soon as they can help me with the flyer. Okay, so if you're working on teams or you're looking for team members, you can look at the sign-in sheet and see if you can find someone to work with, okay? Next, I'm going to go into the notes and the assignment if you don't have any question for me. Okay, so let's share screen. So objective for this week is to work on modular arithmetic and cryptography. So in this week, we're gonna go over substitution cipher with Caesar. And then we are gonna touch, at the end, we're gonna touch on modular arithmetic. So these questions will show up on the final quiz and so on. So we wanna touch on these concepts. We are gonna do the assignments together. And then for the lab this week, you are going to program in C++ for Caesar Cipher. And Caesar Cipher is one dimension, so you can use the concept to apply to Viginere. And then we'll touch on Viginere also I will explain how it works. Then in the next week, we are going to cover relations. You will not have a lab next week, but there is a discussion thread on automata. So, and a quiz review assignment. So you have one more quiz coming up. And then you want to reserve the time. I will be available during lab session in case you want to pop in and have questions. But you can reserve the time to work with your group. And so you should start looking into your projects. And I will, by next week, I will release the final review assignments. This is going to help you prepare for the final exam, which will be multiple choice, and you are required to turn in the course project at the end as well. Okay, so that is the plan for the upcoming weeks. In this week, we are touching on cryptography and modular arithmetic, and we want to explore how to program some of the very basic, right, algorithm, and we're only going to touch on Caesar, but there are other type of algorithm for encryption. So cryptography is important. It's used in everyday's life, from the time that you're using website to access your bank account or sign up for school. When you use HTTPS, that uses TLS. And also if you encrypt files, if you want to send encrypted files across email. So there are different ways that we use cryptography, and a lot of the times you would use web-based cryptography, which is symmetric. And that means that it uses the same key to lock and unlock. So that key is then being exchanged when from the source to the destination. But today, what we're going to do is we're going to look at the very simple shift cipher using Caesar shift or Caesar cipher. So, and to implement this in programming, you would see that we would need to implement modular arithmetic, and we will explain the calculations along with how that will be included in C++ in our lab, the calculation we will touch on today. So Julius Caesar was documented to be the first to use shift cipher, and therefore they named this after Caesar cipher. Later on, this algorithm was then transitioned and transformed into what we see in rotation cipher or ROT and in other form of cipher. So, so what he did was he used the alphabet and he used the letter shifting mechanism to a fixed position down the alphabet to replace the character with the shifted character, so that way it becomes unreadable text. And so with that, he would then tattoo the message onto the messenger's scalp, and he would send the messenger to different part of his army region, so that way the messenger can relay his attack tactics and so on. So here it gives you a little bit of background on how he used the cipher and where it came from. And with the encryption step, what we see is Viginere later on came in, and Viginere cipher is we would do 2-dimension where we would shift across and we would use a key for the column. So what you would see is that Viginere is implementing the shift. And as I mentioned, that ROT13 was a derivative of what you've seen with the shift cipher algorithm. And so it would rotate by 13 places in the alphabet. And ROT was commonly used in the 90s. And there is flaw, of course, in these shift cipher. And then they would then be replaced with newer algorithm, more modern, more secure algorithm. So in the past, we had used Caesar shift with ROT13 algorithm, and that was used for what we've seen back then as Usenets in the 90s. But it is no longer effective as it is very simple. But we would learn from the simple today, okay? So what you see in this table is the alphabet, and you would have from A through Z. And when it gets to the end, if it needs shift, you would then come back to the beginning and begin the process again. So if I'm looking at the letter D for discrete, so this is our plain text. This is unencrypted text or plain text. So the letter D, if we were to shift it right down the alphabet by 3 places, we would count 1, 2, 3. For here's D, 1, 2, 3. So the D is then being replaced with a G, okay? And then the I, if we look at the I and we count 3 places down, J, K, L, so the I would then be replaced with the L. So far we have the D is replaced with the G. It's shifted to the G. The I is shifted to the L. And then the S, if you're looking at the S, you count 3 places to the right, 1, 2, 3. So the S is then being replaced with the V. And then the C, we would come back over here, 1, 2, 3. That will be replaced with the F and so on. Now, in some program, you would see that they don't implement white space and they don't implement symbols. So you would see that that will be the limitation of those program where it doesn't work with the symbol sets. It only works with A through Z, which gives you 26 characters in the alphabet. So that would be the Caesar shift with 3 places. And when we decrypt that message, we would take the letter, the shifted letter, and we would count left. So if you get an encrypted message like this, and you wanted to know what the plain text would be, you have to decrypt it. So G, we count 3 places to its left, 1, 2, 3, and that gives you a D. The L, we count 3 places to the left, 1, 2, 3, it gives you the I. So that's how it's able to decrypt. And decryption just means that it takes encrypted unreadable text and convert it back to plain text where human can read it and understand what it is. Okay. And so this is what we would use with the shift. And so now if we're looking at here, it talks about how we would decrypt it. If we start here, if we shift it, if you go left, it will become this. So for the algorithm for the Caesar shift, what we would have is a function that will be x plus k. K stand for key, and that will be mod 26. And the K would indicate the shift value. So if I'm shifting right 3 places, that will be 3. And the X would be your character to start. So like a D, we would start with the D, right? And so if we're shifting 7 in this example, right, your shift value, your K is going to be 7. And your X is going to be each of the character from the plain text or the unencrypted text. So it will start with the D, and then we count 7 places down, 1, 2, 3, 4, 5, 6, 7. So that will give you a K, and so on. And because the alphabet has 26 characters, we would use modular arithmetic, or use mod 26 to give you the actual shift value in that particular program. So if you wanted to shift 7, you would implement the shift value. And since our alphabet has 26 characters, then we would use mod 26. Now, if you're looking at Latin or other type of alphabet, you have to consider that their character sets are different, right? So in English, we would have 26, so we would apply the mod 26 here. Now, consideration on how our program is going to produce the shift, we would think about our encoding and the way that we would see, right, UTF-8 or Ascii. Ascii is limited in that there's a ceiling in Ascii for the sets. So if you're looking at, for example, if I search for Ascii Table, if I go here for the website, you would see that here is there is decimal equivalence, hexadecimal equivalent, octal value, and the actual character. So when we're looking at the capital A, right? Okay, the capital A, the decimal equivalent of that is 65, the hex is 41, and the octal is this, okay? That value is then different than the lowercase a, which is then decimal equivalence is 97, hexadecimal is 61, and octal is 141. So in your C++ compiler, it's able to convert it, right? It's able to understand that when you put in a certain value, like decimal is 97, it's going to know that that's equal to A. Now that can be different when you compare that to other encoding schematic, other encoding scheme, where we would have an encoding system like UTF-8, where the range of the characters would be wider. So you would often see that when we're using symbols now, right, character sets needs to be larger to implement symbol. So when you're looking at Ascii, you are limited with very few symbols, okay? So for the Ascii conversion in some program that you would see that it has limitation is because it's using Ascii, that it's only able to have some of the symbol, but not all of the symbols, right? We would have some of the basic symbols, some of the arithmetic operators, but you don't have the entire set of additional symbol. And then when you're looking at the extended ASCII sets, right? When you're looking at other type of alphabet, for example, if you're looking at French, Latin, I speak Vietnamese, I write and read a little bit of it, and we use, right, letters with accent on the top like this. Or in Spanish, you have the ñ, right? So you would have some extension to the ASCII code, but your basic ASCII table, it would be here, right? Decimal 127 would entail this. So now not all compiler is able to interpret the extended ASCII codes. So because it's not commonly used in the English language, so therefore when they created the compiler, they don't include the extended ASCII code, okay? But then you also have UTF. Like I said, the character sets range is wider. And so you would then see that would be commonly implemented, right? When we need to use additional symbols or characters that are above the ASCII range. Okay. So if you want to, you can refer to the Ascii table so you can see the equivalence. I don't know if I have shown you this. I think I have. But in my assembly class, we regularly visit this because a lot of the assembly language uses Ascii and we need to Ascii convert it. Okay. So here it talks about encoding, and encoding is a way that we would use numbers instead of letters. And so we would use some values that would represent that particular character, right? And remember that the computer, we talked about binary in the beginning, it is a calculator, right? And it only adds. So we would then, if if we give a value to a certain letter, we would then tell it that this is equivalent to a certain character. Then with that encoding system, we're able to translate, right, to convert that character to that value so it can quickly compute. Then, so in that, we would see that we can encode your plain text or your characters by replacing the letters with the numbers. And this is a system that we agreed upon, right? That will be standardized across. So that way everybody in the world will be able to use that system. And so that way we can have a standard output for, web, for internet resources, and so on. So then a way that we can set it up would be like this, where the A is going to be 0, 0, the B is going to be 0, 1, and so on. And by the time we reach Z, we would have 25. And in this case, we're only encoding for the letters in the alphabets. Okay. So if we take that and we convert our plain text to the encoding values, then we would just use the numbers. Like it says math is cool, it's going to become these values where the M is 12. So you would see 1, 2 represent M. A is 00. And then T is 19 and so on, as you can see. Okay. All right, so let's practice using Caesar Cipher. So in the first question, it asks you to use Caesar Cipher, substitution cipher. And we wanted to shift the letter 7 places to the right. And we want to input the shifted. You can put it in the row or you can just type it out like I have. So what I did was I start with the C. And we would count 7 places. 1, 2, 3, 4, 5, 6, 7. So the C becomes the J. So the first letter is shifted to the J. The O, you can count it. 1, 2, 3, 4, 5, 6, 7. So the O becomes the V. So we can put the V is substituted for O. The M, that would be from M, 1, 2, 3, 4, 5, 6, 7. That becomes the T, and so on. So for the 2 words computer science, and they're all capitalized here, we would have JVT, WBALY space ZJPLUJL. Okay. Now, what happens when you get to something down the alphabet? What if your plain text contain a W, right? Then what you do is you're going to count it and wrap it back over here and continue to count. So for example, if my plain text contain a W, I would go 1, 2, 3, 4, back to A, 5, 6, 7. So the W becomes, it's shifted to a D, okay? So when it reached the end of the alphabet, it's going to come back to the beginning and we would continue to count the shift values, okay? So that's why when you get to the T here for computer, for that T, you notice that it becomes the A because when you get to T, if you count 7 places, 1, 2, 3, 4, 5, 6, 7, it's shifted to the A. Okay, so when it reached the end of the alphabet, we're going to come back to the beginning and we will include that with the shift value. Okay, so our encrypted text using Caesar would be this for computer science. Now you would see there are online tools, right? Of course. And somebody programmed that, like how you would create a program. You would ask the user to input the text, right? Put in the key shift value and then implement that with the algorithm and then show the output. Okay. Now, there are several approaches as you would see on Wednesday, as in do we use char? Do we use string, right? And when you use a string, you would treat it as an array of characters. Or when you use char, then you would then be able to actually just add the shift with each of the character. So it really depends on the programmer approach, and we'll take a look at some of those approaches on Wednesday. Then for 1B, we would take keeping secrets. And the downside in substitution cipher is that you notice that we can start seeing, right, repetition of the characters. So when I teach encryption to security students, the downside in encryption is that there are known good keys, and so they can match it, and they can use, in the case if we're looking at like wireless, they can use like rainbow attack too. So they would have these tables of like known good encryption keys, and they would be able to match it. um, so your encryption is only as good as how your key would be, and the algorithm of it. So key length, algorithm, those are the things that we consider for encryption. Um, because a lot of people, when they think about encryption, they just think about like the algorithm of it, but it's actually the most important area is how you protected your key and how the key is generated and exchanged, and that really elevate the security side for encryption. The whole point is to really protect the integrity of your plain text message. Is when you encrypt, you make it unreadable so other people cannot see what it is. And so that way, you're keeping that secret, and that's important. Okay. So when we do this, when we do this phrase, keeping secrets, you would start with the K, and you're going to shift right 7. So 1, 2, 3, 4, 5, 6, 7. So the K becomes the R. The E, if we count it to 7, we would have L. And as it repeats, you would have LL. P becomes W. And then I becomes P, and so on. And like I said, when you get to the end, like the T, you want to wrap it around at the beginning. And we already solved for T from the last one. So the T, when it shifts 7, it's going to become A, and so on. Okay. So this would give us keeping secrets when it shifts 7. And it doesn't always have to be 7, right? It could be 3, like what you saw in the example, or a 6, or 5, or 13 was the common thing for ROT back in the 90s. Okay. So after you finish that one, you will have to do C on your own. So you would start with C, and we're going to shift 7. So count 7 to the right. 1, 2, 3, 4, 5, 6, 7. So C becomes a J. And then you can go with H, and so on. So we want to make the phrase change the world by doing substitution cipher. You can type out your answer here. As you already have some of the shifted value, right? Like T, E, you can refer to the last one, so you don't have to repeat the count, and so on. So make sure you put the answer for C there. Any question with exercise 1? So what we're doing is we're looking at the actual physical, the mechanical piece of this, right? So when we program it, we can actually see it, because the computer, it's going to shift for you, and it's going to substitute the value for you. So if we do it manually, we can understand how that's implemented and how we would program it. Okay. Okay. Now, oops, I'm sorry. after we encrypt, okay, we would then decrypt by going the opposite way. We would count left and we would replace the character with the substitution character after it landed on the shift value, right? So for number 2, we would shift left instead of right because now we are decrypting. We're going to take encrypted text and we're going to convert it back to plain text or unencrypted text. So we would start with the Z and we're going to count left 7. 1, 2, 3, 4, 5, 6, 7. So it landed on S. So we put the S. And then next we're going to move to B as it is at the beginning of the alphabet, and we count left. So we're going to wrap it back to the end of the alphabet. So we have B here. We're going to go A as 1, Z as 2, Y as 3, X as 4, W as 5, V as 6, and U is 7. So we got the U shift for B. Then J, if we count left, 7, 1, 2, 3, 4, 5, 6, 7, we would land on C. So JJ becomes CC. And then the L would become the E. The Z is going to give us S. So ZZ is going to be SS. F is the substitution for M. And B, that will be your U again, because we found that earlier. And then your S is going to become the L. So when we solve this, as we count left with 7, we would have successful protection for 2A. And this is shifting 7. So when we decrypt, we got the plain text back. Any question with decryption? So as you play with this, you can see how we can go from, for number 2, we would go from encrypted text to plain text. Okay. And you can solve for B for number 2. So we would start with the L and we're going to count left 7. So 1, 2, 3, 4, 5, 6, 7. So you have an E. And then your U, you can also refer to the last one. When we did the U, that's going to be the N, and so on. Okay, so you can solve for that. It's not too bad. Any question? Okay, so this shows us how to decrypt. And then we'll work on encoding shortly. Now, while you work on that, as I mentioned earlier, I mentioned the word symmetric key, right? It's just to give you a little bit more detail. So when you watch tutorial video on encryption, I put some links into your Canvas module. So symmetric key is, as I explained earlier, we would use the same key to encrypt and decrypt. And when you, let's say that I want to encrypt a message and I want that message to go to you. So what I would do is I would generate the encryption using a key. And then once it's encrypted, I need to be able to provide you with the key so you can open it and decrypt it, right? You can use that key to decrypt it. So it's kind of like if you lock a secret box with that key in order to see what's in the box, you have to use that same key. So symmetric key type of encryption uses the same key. Now, sometimes uh, in nowadays in the modern world, right, we would so what happens when that key is intercepted, right? What if somebody intercept and get that key? Well, we have ways where we would generate a one-time use key, or in some cases we would then, that key would then be regenerated, or it could be randomly generated. um, so that way, in the case where if the person, if an attacker or somebody trying to intervene and get that key, they won't be able to solve it, right? Symmetric key based encryption is very, very common. Most of the stuff that you use on the internet, right, all the website that you use with the encrypted sessions, it uses symmetric. And web-based encryption is a stream encryption where it encrypts one bit at a time, because in web content, and when we look at web content, um, it's sometime we don't know what the data size would be. So it is more feasible to implement streaming where it's going to do encryption one bit at a time, compared to something that you would see if you hear a lot about, like, blockchain with cryptocurrency and all of that, right? um, in a lot of, in other type of encryption, is that it's going to chunk the data into chunk size, or what you would see in blocks, right? Hence the name blockchain. And then it would encrypt it based on the type. If you implement the algorithm, it would chunk it, let's say 56 bits, then the chunk size would be 56 bit. And what it would do is when it encrypts that, it uses XOR logic gates um, to be able to generate additional bits that's going to group the chunk together. So when it decrypts, what it does is it's going to decrypt each chunk at a time, and it would decrypt in chain. So that is a lot slower, but is secure. So when you hear all of these things about blockchain, right? Blockchain is not known for performance, because it requires time to really process that. It requires a lot of processing power. So now, compared to something that's quick and fast and convenient, that will be stream encryption. And stream encryption, for web-based purposes, we would use symmetric key. So that gives you a little cliff note on encryption. Um, but you know that university, they would spend a whole course just talking about encryption and how to develop encryption cryptography algorithm and so on. Okay. Any questions? Okay, then next we're going to talk about encoding messages, giving the table, right? So I highlighted in different color, so that way you can see how the encoding would work. So we would start with A, take on challenges. So we would go to T, that gives us 19. So you type in 19. And then A, that gives us 00. So you put 00 for A. K, you go to K, that gives us 10, so 1, 0. And then E, which is 04, so you type in 04. So this represents take, okay? And then since we have a space, we're gonna put 26, okay, even though it didn't include that in the table. So after Z, we would have 26 for space. And then we would have on O, that's gonna be 14. And N, that's gonna be 13. So O is 14 and N is 13. And then space, 26. And then C, which is 02. And then H, which is 07. A, 00. L, 11. L again, 11. E, 04. N, 13. G gives you 06. And E is 04 and S is 08. Okay, so altogether, this length, this entire set, right, these group of numbers gives us take on challenges encoded, given the encoding scheme as the table. All right, in the next one, you would need to solve top secret using the encoding, just like what we did before. So I started it for you here. T, you have 19. T for 19, so put 19. O is 14. P is 15. And then space. And then now you just gotta solve for secret using encoding. So look at SECRET. Add those numbers. So in this one, instead of shifting, right, for the encoding, we're just replacing that character with a number. Any question? Okay. All right. Let me know if you have any question. Okay, good. Okay. So we are just doing encoding for number 3. And let's talk about one-time pad. So after the section on encoding in your notes, it goes into OTP. And OTP sometimes is referring to as Vernam cipher. Okay. And this is a crypto algorithm in that plain text is combined with the random key. And it is only existing mathematically unbreakable encryption. It uses special operation. It uses, government uses this for, to send messages during the war. It uses with the intelligence agency uses this. So historically, this has been used quite a bit. And even in current technology, you would see OTP being implemented in some encryption software. So for example, if I want to encrypt email messages, I would download an encryption tool like encryption software that would encrypt email messages, and some are better than other, right? Um, so you would see some software incorporate OTP. So one of the things that we wanted to note is that the key is as long as the message of the data. So if your plain text is long, right? Let's say I have 250 characters for my plain text, then my key length will be as equivalent. Okay, so your key length is as long as your message data. And the key is truly random, not generated by a simple computer function. So it is not pseudo-random, it is truly random. And key and plain text is then calculated using mod 10 for the digits, mod 26 for the letters, and mod 2 for binary. So it uses modular arithmetic. Whenever you deal with encrypting digits and letters, you often see that they implement modular arithmetic. So 26 for the English alphabet, 26 characters, 10 for 0 through 9, and modulo 2 for binary. With the name, we see that the key is only used once. So when the sender and the receiver they would then, it's only one time use. So after it's used, it's then be destroyed. Okay. So with the software application, that key is generated, it's used to encrypt or decrypt, then it's gonna get removed or deleted. There should only be 2 copies of the key, one for the sender and one for the receiver. And in some software tool it does allow where you would then generate keys for multiple recipients, but usually it's 1-to-1. Okay, so you can read more about one-time pad, and I know Khan Economy explains also one-time pad there. So in the next question, we can answer the next question now. Describe the one-time pad ciphering method. It uses random key. Key is used as long as the message is sent and received. Sender and receiver hold key, and it's ideal for one-time use. Now in OS, right? Each OS has its own encryption tool that's built in. For Windows, right? It uses NSF. And encrypting files is different than encrypting the entire drive. Like Windows uses BitLocker to encrypt the whole drive, whereas files you would right click the folder or the file and then you would choose the option encrypt, and that uses NSF. Now in Linux or Mac OS, you would see that it's different, right? And that's native to the operating system. We're not talking about third-party applications where you would download and install, and that's separate. That's considered third-party application. So any question with for OTP? And you can refer to note page if you wanted to get more definition and benefits of features of OTP. So for Viginere, this is part of your project, right? There are many tutorial videos on Viginere. Some are better than other. But this cipher was invented in 1586. And with the reciprocal table of 10 alphabets. So the version of this has transitioned, but the main area is that it's require a key, and that key is used to correlate with the actual ciphering. It does add to Caesar cipher in that there is an additional dimension in how you would use text string as a key instead of a number to shift. Okay. And it uses that key to implement the shift as a second dimension. So what do I mean by this? When you're looking at this is going to look very similar to what we've seen with the Caesar shift. We are still using the alphabet. Okay, so we would have mod 26, but the key, instead of one value as a number, like shift 7 or 3 or 6 or 13, right? You would have a string that would be required for the shift. Okay, so you would have a character per shift. So here it talks about what Viginere is and the equation for Viginere. So to encrypt the letter, we would write the key underneath the plain text, and we would take the plain text letter at the top and the key letter on the left. The cross section of those letters will be your ciphertext, so you would cross correlate it. Okay. Then the first letter in the example below, crossing between the T and the X. So let's practice. Okay. So you would have, this is your plain text. This is a secret, or this is secret. And your key is this. Okay. Then what we would do is we would take T and X. Okay. So you would go across the column to T and then down to X. Let me scroll down a little bit so you can see. So here's my T for my plain text. And then I'm going to go down to X. Okay. And that will land on Q. So when you encrypt T with the key, it's going to give you Q. Okay. Then again, we would do that with the H. So you would go across for H, and then you're going to go down to V. So from H, I'm going to come down to V. Okay. And then that is going to give me C. And then I, we're going to go across for I. And then we want to come down to H. Okay. Which gives you a P. So from I, if we go down to H, that lands on P. Okay. So it's different than Caesar cipher in that we're using the key character to correlate with the plain text character that's going to give us the ciphertext. And that's Viginere. Okay. Now the downside of this, if you notice, if you look at A, right? When you have an A with an A is an A B with an A is a B, a C with an A is a C, and so on. So anytime you have an A in the mix, you get the same. Okay? And then anytime you have a Z, it's the reverse. So Viginere is not, of course, far from perfect, but it is it is elevated from Caesarship. So then here it talks about how your key can be generated, it can be automated, it could be one-time use, and we would use that key with our plain text to get our cipher. Okay. Any question on Viginere? So here it touches back on the shift with Caesar cipher. So let's do some practice with Viginere on this one for number 5. So we are going to use Viginere cipher and we want to determine the encrypted message given the plain text and the key. Okay, so if you get earn, which is shorter than your plain text message, what happens is it's going to repeat, and it's going to repeat that key to match up with the length of your plain text message. So when your key is less than, the number of characters of the key is less than your plain text, it needs to extend it, it needs to repeat it and fill it and make sure that it becomes the same length as you can see. So when I say graduation is near, my key is earn, and I would have earn repeated to extend to be equal to the length of my plain text. So I would start with the G. So you would go across the column to G, and then you would come down to E, and you would get a K. It would land on the K. Okay. So you use your key for row, and you use your plain text for column. And when it cross section, that's going to be your encrypted text. So K. And then I go to R. So across to R, and then I'm going to come down to A, which is R, right? Earlier I said that anytime you have the A in the key, it is the same letter as your plain text. And then if I have the A for my plain text and I need to go down to R, it still is the R. So R. So in this case, the plain text is A and the key is R, it gives me R. You see? So anytime you have the A in the mix, you would get the equivalence of one or the other. Okay. And then D, we're going to come across to D, and then you're going to come down to N. Okay. Which gives you Q. And then U, go across to U, come down to E, and I have Y. And then you can solve for the rest. Okay, so your plain text is going to be for the column and the key is going to be for the row. If it's short, you want to extend it to the length of the number of characters in your plain text. And that's how you have Viginere cipher. Any question? So as you do this, think about how you would program it. Okay. Think about how you would program Viginere in C++, the functions that you want to implement. Of course, you need to do mod 26, right? Because we're using alphabet. So how can you implement the input of the key, right? You want to ask the user to enter a key, enter the plain text, and then enter the key, and be able to adapt the key to the shift or the cross correlation with the plain text. And some group had turned in char for the data type that they use. Some group, they use string objects. Some are better at handling space and symbols, and some does not. Okay. Okay, any question with 5? And then you can do 5B as well. Mask, plain text, and secret. And again, we wanted to extend it. Secret to match up with our plain text. It is secret. Yeah. So you keep, so let me double check. Hold on one second how I put it for you. I might have omitted the S. It's secret with no S, just secret. So the reason why we repeat the S is because it needs to extend it to the rest. So you have secret, 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 and it needs to match up with the same number of characters with your plain text. Okay, so no S with the original key. So the way I had it was I had to extend it, right? And then you can count up the character 2, 4, 6, 8, 10, 12, 13. So we just got to make sure it's 13 character, 2, 4, 6, 8, 10, 12, 13. Yep. So it will be like that. Question? Okay, very good. Thank you. Good job. You know, if you like programming encryption, there are tons of companies that hire for this area. Engineers for, you know, security company, they have engineers that does crypto analysis that do reverse engineering and some of that, especially when we deal with like stuff like ransomware, where it encrypts data. And, you know, that way they would study that they would analyze that type of stuff. So, um, very interesting area. Okay. All right. So let's talk about the next part. If you're done. Okay. So here it shows you how we would look at linear cipher. And when we were looking at, as I explained earlier, so when you're looking at the equation, you would have A's. A is going to be M times A plus K mod 26. Okay. And M is going to be 5 as and K is going to be 11. So they would supplement this, or they would substitute it into the equation. And so that would have two different letters, always with the two different cipher letters. So then we would consider how that would be using the encoding with characters. Okay. Is it going to be, is space represent space, or space represent another letter, or is it shifting as how it would treat space, right? Are you treating space as an underscore, and so on? Okay. And so here it touches on some of the questions that you can think about when you think about linear functions with substitution cipher. And as you saw in the equation, we're using mod. So mod function is used quite a bit. You saw it, it's in cryptography. It's used for calendars, for clocks, for random number generator, for hash tables. So then we would use mod functions. And in our case, when we look at Caesar cipher or shift cipher, we would implement mod with our alphabet of 26 character. Okay, so we would say A mod n, where A could be any integer, and n is an integer that is greater than 1. Okay, and A mod n is defined as if n is negative, then we are restricted because we said that, oh, n needs to be greater than 1. So how do we handle for integer between 0 and n minus 1? Okay, so in the next part, we're going to look at how to solve for a modulus. So when we say 17 mod 5, we would take 17 divided by 5, which gives you 3 as a quotient and 2 as a remainder. So the answer for this is the remainder value, which is 2. So when you're using mod, you're looking for the remainder value. Okay. So when we say 17 mod 5, we would get a 2. So that means that we would take 17 divided by 5, which is 3 as a quotient, and your remainder is 2. When we do an 8 mod 5, we would take 8 divided by 5, which gives you 1 as a quotient and 3 as a remainder. 55 mod 5, it divides evenly. So if you take 55 divided by 5, you get 11 and 0 as a remainder, as it divides clean, right? No remainder there. Now 4 mod 5, if you take 4 divided by 5, right, you get 0 as a quotient and 4 as the remainder. So that's just a little bit of review for those of you who forgot about mod from your C++ CS5 class or even other classes, right? Then if we take 37 mod 17, we would get 3 because 37 divided by 17 gives us 2 as a quotient and 3 as a remainder. So a very basic exercise on mod. Okay. Now we need to think about how we would evaluate A mod n when A is negative. Okay. So as long as n is greater than 1, the values of A mod n must be between 0 and n minus 1. So in general, A mod n is a unique integer between 0 and n minus 1 in that A is equal to Q times n plus A mod n. We cannot forget the mod n. I should highlight that. Okay. For some integer for Q. So when we take it and put it into this format, right? If you're thinking about 17, negative 17 mod 5, right? Let's not look at the negative here. So when we look at only negative 17, that's going to be negative 4 times 5 plus 3. And then we got to throw in the mod 5, right? Can't forget that. Okay. So this is going to give us negative 20 plus 3, which gives us negative 17, right? So negative 17 mod 5 is going to be negative 4 times 5 plus 3 mod 5. And of course, you can use your calculator for this, but I want to show you the breakdown of it so you know. Okay, so when we're looking at negative 8, that breaks down to be negative 2 times 5, which gives you negative 10 plus 2. So if we're looking at negative 8 mod 5 is going to be negative 2 times 5 plus 2 mod 5. Okay. So again, see, it just gives you the negative 55, what that equals to, negative 4. And you can always check with your calculator and make sure that you're getting the right result, because sometimes it does get confusing when we go into power. Okay. All right. So let's do the next one. For number 6, we would look at the mod function definition and we would solve this problem. So 80 mod 3, you would take 80 divided by 3 gives you 26 as a quotient, and remainder is going to be 2. So your answer will be 2. And then if we take 120 mod 14, you would take 120 divided by 14. Okay, you can do the long division if you wanted to check this, but you should get 8 as a remainder. And then for C, we would take 975 mod 2. Anytime you have an odd number and you mod 2, you know the remainder is going to be 1. So you can check it. So 975 divided by 2 should give you 487 as a quotient, and your remainder would be 1. So the answer is 1. For number 6, D, you can solve for it on your own. So we can take 461 divided by 3. right? Which gives you what? 1, 4, 143 with the 2 remainder. And then the same thing for the next one. So 726 divided by 25, you're going to get a quotient, and whatever the remainder is, you would have the output value. Okay. So make sure we know how to find the result for when we're using mod function. Okay, question. So 6 is pretty easy, just a warm up for modular. And for your calculator, right, if you're using your calculator, just go to scientific mode, and you have the mod there, so you can check your answer. Okay, so let's talk about the next one. So before we hit 7, let's cover some additional concept. We still have some time. So here it shows you how to do negatives. Okay. And let's take a look at the property of mod. It says let n be integer that's greater than 1, and let a and b be any integer. Then when you have a mod n is equal to b mod n, then the integer k would be a minus b is equal to k times n. Okay. So with the mod property, when you have a plus b mod n, through the distribution law, you would have a mod n, b mod n, right? You're going to add that, and then mod n. Okay, so you got to distribute it out. So you have a mod n plus b mod n times mod n. Okay, so that's addition. Then when you multiply, same law that would be applied. So you have a times b mod n, then you would have a mod n times b mod n, and then mod n. And then we saw negative earlier. When you have negative a mod n, then that's going to be equal to n minus a mod n. Okay. So in this example, let's say that we have 14 plus 17 mod 5. That we would distribute it out. We would have 14 mod 5, right? First number, mod 5, plus 17 mod 5, and then mod 5 times mod 5. So that would give us 14 mod 5 on the inside, this right here, okay? Plus 17 mod 5, this right here, then mod 5. So if you take 14 mod 5, you would get a 2 as a quotient, 4 as a remainder. So 4 is the answer for that. 17 mod 5, you would get a 2 because 17 divided by 5 is 3 with the 2 remainder. So you would take this, add them together, which inside the parenthesis, we operate that first. So you would have 6 mod 5, which gives you 1. Okay. Question. So on page 7 of your notes, it gives you the example that you can refer to for your assignment. And take a look at the next example, where we multiply. So when you have A times B mod C, that will be equal to A mod C times B mod C. Keep it inside the parenthesis and then mod C on the outside. So let's say that if we do 4 times 7 mod 6, right? You would then need to break it to 4 mod 6 times 7 mod 6 times mod 6, which gives you 4. Okay, 28 mod 6 is 4. Okay. All right, let's try. Exercise. Oops, sorry. Exercise 7. So you're given A plus B mod C is equal to A mod C plus B mod C mod C. Tongue twister. All right, so we would get, for A, we would have 15 plus 16 mod 7. So then you would distribute 15 with mod 7, 15 mod 7. 16 here, we would take 16 mod 7, distribute that with the mod 7, keep it inside the parentheses, and then we would apply the mod 7 on the outside. So 15 mod 7 gives you 1, right? Because 15 divided by 7 is 2 times, so 2 as a quotient with 1 as a remainder. 16 mod 7 is going to be 16 divided by 7, also 2 times with 2 remainder. So you would have 1 plus 2, which is 3, mod 7, which gives you 3. Okay, any question on 7A? Then when we look at B, I typed it out for you already, but you can practice on your own. So 10 plus 29 mod 4. So we would then distribute the 10 with the mod 4. So we would have 10 mod 4 plus, and make sure we apply the parentheses accordingly, otherwise it doesn't operate right. 29 mod 4. Keep it inside the parentheses, and then we would have mod 4 on the outside. 10 mod 4 is going to give us 2, because 10 divided by 4 is 2 times with 2 remainder. So 2. 29 mod 4. 29 divided by 4 is 7 times. So 7 as a quotient with 1 remainder, because 7 times 4 is 28. Right? So 2 plus 1 is going to give you 3. Then you're going to mod 4, which is 3. So when it's less than your mod value, it is the remainder. This is super easy. Okay. Question. Okay, then you do C. Distribute it out, and then don't forget about the mod on the outside. Operate what's inside the parentheses first, and then apply the mod on the outside. Okay. So after this week, we should know how to do modular arithmetic, addition, multiplications, even power of mod, which we will cover shortly. All right. Any question with 7A, B, or C? Next, we're going to look at multiplication. Same approach. So we would say that given A times B mod C, we would have A mod C times B mod C, keep it in the parentheses, and then we would mod C on the outside. So let's solve for 8A. We would have 18 times 11 mod 5. So first you want to distribute the first number with mod 5 here. So 18 mod 5. And then you would take 11, distribute it. So use distribution law, then you would have 11 mod 5 with associative law. I didn't include all of that. But so then you would have mod 5 on the outside. Okay. So then 18 mod 5, 18 divided by 5 gives us 3 times with 3 remainder, so 3. 11 mod 5, 11 divided by 5 gives us 2 as a quotient with 1 remainder, so 1. Then you operate what's inside the parenthesis with the multiplication first. So 3 times 1 is 3. Then you're going to mod it on the outside. We can't forget that. So mod 5 again, 3 mod 5, which gives you 3. Okay. So very similar to what you've seen with the addition for modulo. Any question with 8A? Then I also help you with B. So again, we have 33 times 22 mod 4. So we would take 33 and make sure that it's distributed with mod 4. Take 22, so we would multiply it by 22 mod 4, distribute with mod 4 here for 22. And then we cannot forget about the mod 4 on the outside. So then we would first need to operate what's here inside the parenthesis first. So 33 mod 4, that will give you 33 divided by 4 is 8 as a quotient with 1 as a remainder. So 1. 22 mod 4, 22 divided by 4 gives you 5 as a quotient with 2 as a remainder. So 1 times 2. So multiply this gives you 2. And then we would do a mod 4 on the outside. So 2 mod 4 gives you 2. Okay. And then you can try C on your own. So take 15, mod it with 2, times it by 27, mod 2, and then mod 2. And then find the mod from the inside, the parentheses, multiply them, and then mod 2. So make sure we know this for the final and the quiz. You will be given problems like this for our next quiz and the final exam. Okay, so ask you to solve and then you have to select the appropriate answer. Any question with 8? only got a little bit more to go anyway, so you're almost done for today. So don't forget, we do have a lab this week. Okay, starting next week is when we don't have lab, but so make sure that if you need help or have questions, make sure that you attend lab and so we can work on it. All right. So solve for C, you can write it out and then pretty easy. So before we work on 9, let's take a look at our notes. Here it also shows you how you can use the plus times table for modulo and the type of rules that would apply for modulo. Next, we're going to cover powers of mod. And just to kind of bring back to what we talked about with encryption earlier, if you ever use RSA, which quite a bit in Linux, it's everywhere in Linux, right? If you use Raspberry Pi authentication, it uses RSA. If you use AWS, it uses RSA. It's implemented quite a bit nowadays. So RSA stands for Rivas, Shamir, and Adelman. And this is the first PKI or public key crypto systems that is for data transmission. Okay. And it uses, they call it public key, but it's actually using a key pair. So if the data is encrypted with the public key, it would require a private key to decrypt. If the data is encrypted with the private key, it needs the public key to decrypt. Okay, so this is what we call asymmetric key encryption, where it uses one key to lock and the other key to unlock. And with RSA, because asymmetry, the asymmetric key, this is based on the factorization of the product of two large prime number, and it plays on the concept of prime number is harder to generate further down the line. So you would then, for computational power purposes, right? In that this is a strong encryption that it uses the factorization of the product of two large prime number. And that's the algorithm of this particular encryption. Okay. Now it says that anyone can use the public key to encrypt the message, but with the current published method, the public key is large enough only that someone with the knowledge of the prime number can decode it, the message feasibly. So can it be decoded? Sure, it can if you can figure out the calculation for the prime. Okay. This is considered a slow algorithm. Okay, but our processor is now good enough to be able to use this. So you often see RSA being used for authentication quite a bit now. Okay. RSA passes the encrypted share key for symmetric key, and public key is shared, but the private key is kept. So even if the public key is intercepted, it cannot be decrypted without the private key. Okay. So in that, we would see that it would implement what we now would learn as the power of mod. Okay. when the exponent is then itself a power of 2 by using the property. So earlier we learned about multiplication, where we would have a times b mod n would be a mod n times b mod n mod n. So if you look at where power would represent the number multiplied by itself several times, okay? So if we take this and we break it down, and looking at this example, if you have 2 to the 90th power is equal to 2 to the 50th times 2 to the 40th. So if we say 2 to the 90th mod 13, that will be equal to 2 to the 50th times 2 to the 40th mod 13. Okay. So then we would solve it based on what we just learned earlier. We would have 2 to the 50th mod 13 times 2 to the 40th mod 13 mod 13. Then you solve for the inside here. So that is going to give you 4 times 3 times mod 13, which gives you 12 mod 13, which is equal to 12. Okay, so that's one example. Another example that's shown here. So when you have 37 square mod 3, that's equal to 37 mod 3 squared, which is 37 mod 3 times 37 mod 3, right? Which is going to give you 1 squared or 1. And then also another example like this, where you would have 115 to the 32nd mod 7. That will be 115 mod 7 raised to the 32nd power, which is equal to 115 mod 7 to the 4th times, and then raise that to the 8th. So multiply it by 8, which is 4 mod 7 times 8. Okay. And then that will be 16 mod 7 to the 4th. So we want to simplify it, and eventually we would get down to from 2 mod 7 to the 4th to 16 mod 7, and then eventually 2. Okay. So we would use modular multiplication rules. When you have a squared mod c, you would have a times a mod c, which is a mod c times a mod c mod c. Okay. And that will be the easiest format that you can follow, or in some cases you can apply the multiplication of power on the outside there. Okay. And so this is an example for this. Now, of course, the calculator can produce it for you, but you want to be able to break it down so that way you understand what's happening with the modular arithmetic, with the modular multiplication when you're using power. Okay. So let's try. We have an easy one to solve. Okay, so for number 9, we are given a to the m mod n is equal to a mod n to the m mod n. So when we have 3 to the 6 mod, 4 to the 6 mod 3, that's really 4 to the 3rd mod 3 times 4 to the 3rd mod 3. Or we can also say 4 times 4 times 4 times 4 times 4 times 4, right? Mod 3. Okay. You can also break it down like other ways. We can do it like this, right? So 4 to the 3rd mod 3 times 4 to the third. Oops. Mod 3 and then mod 3. Or you can have it like this. Okay. So when you have it like this, what you will see is that you would multiply it, right? And then, so that would give you 4 mod 3, which is equal to 1. Because 4 mod 3 is 1, right, to start with. And then if you multiply that again and multiply that again, so you're going to end up with 1. That's really equal to 1 times 1 times 1 times 1 mod 3, which is 1. Okay, so what I put down here is that we would then look at 4 mod 3. What is it equal to? That's 1. And so basically it's 1 times 1 times 1 times 1 times 1 times 1 mod 3 for these right here. And then that would give us 1 mod 3 or 1. Another way that we can write it is 4 mod 3 times 4 mod 3 times 4 mod 3 times 4 mod 3 mod 3, which is also 1. So however you look at it, you still should get the same answer. Okay? Any question? Okay, so for B, we are given 18 to the third mod 7, and 18 mod 7 alone, we would have 4. Okay, so first you gotta take a look at what 18 mod 7 is. That will give us 4. So 18 to the third represents 18 times 18 times 18 mod 7. And just like what we've done before, we distributed it out. So we would have 18 mod 7 times 18 mod 7 times 18 mod 7 mod 7, which gives you 4 times 4 times 4. For each one, it's going to give you 4, right? Remember, we found that here. So that will give you 64 mod 7, and 64 divided by 7 is going to be 6 times with 1 remainder, so 1. Okay. Any question on 9B? And you need to solve for C on your own. Just like what we've done with 18 mod 7 here, you can do 22 to the 4th mod 9. So that's equivalent to 22 mod 9 times 22 mod 9 times 22 mod 9 times 22 mod 9 mod 9. And then find each one, multiply them together, mod 9, and you have it. Okay. And whatever result you get, it should match with, if you check it with the calculator. If you're off, then you missed something, or you didn't multiply it or mod it right. And that concludes my power for mod and the lesson. So make sure that we solve for C, put all your answer on your document, save it. If you handwrite it, you can scan it, take a picture of it, whatever you want, as long as I can read it. The only thing that I haven't put in for some of you that submitted extra credit, I'm sorry, is your uh travelers to Hawaii problem that you solved a while back. Okay, I gotta add that. I have to turn on the assignments and I will add that manually. And congratulations, I think Mario won the last review game, if I'm correct. Yep. So I will send Mario a gift card tonight. I forgot about it last week. Actually, I didn't. I just got really busy and I haven't had time to do that. So if you have time, if you want to read, you can read the next chapter, or work on your project, or if you have anything missing that you want to turn in, make sure that you work on that. Okay. And then I'll see you here on the 5th, which is Wednesday, for our lab. That will be our last lab. Oh, it's so fast. I remember I started having you the first day not too long ago. But anyway, it's close to the end now, so I'm going to give you some time to work on your project. Okay, put your name into the chat. If you're finished, if you have question, you can stick around. I will address some questions. Have a good night.